In 1928, Paul Dirac derived an equation predicting something that was proven soon after. All particles have an antiparticle version of themselves, identical except with opposite charges and a few other properties. We now know that when a particle collides with its antiparticle, they annihilate to form pure energy. Sounds crazy, but Einstein already showed us that matter and energy are intimately related. Now let's think about that process in reverse, the conversion of energy to matter. When this happens, equal parts of matter and antimatter are formed, as you might expect. What's weird is, if all of that's true, we would expect the Big Bang to have created equal parts of matter and antimatter, and for all of that to have then annihilated. Obviously, that's not the case, since when we look around, most of what we're seeing, pretty much all of it, is matter. Any minimal amounts of antimatter produced by decay or other processes on Earth are quickly annihilated. So where is all the antimatter? Maybe we're just in a pocket of the universe where we can't see any antimatter, and it's actually just hanging out somewhere else. Yeah, most scientists can't get behind that idea either. So what could have caused matter to have been favored during or immediately after the Big Bang? While no one knows for certain, physicists around the world are on a relentless search for some type of answer. One thing that could play a role in the abundance of matter is if some particles behave slightly different than their antiparticles, and this has been shown to be the case through experiments dating back as far as the 60s. Kaons, or K-mesons, mesons just being a quark and antiquark combo, were the first to show a slight difference in behavior, defying what we previously thought about particle and antiparticle symmetry. Physicists have more recently uncovered a couple more types of mesons that have particle and antiparticle behavioral differences. The issue here is, most agree that these differences aren't enough to account for the observed difference between matter and antimatter. There is some evidence from an even more recent experiment in Japan that neutrinos, our favorite ever-elusive, nearly massless particles raining down from the sun, could have a role in this matter-antimatter mystery. We've known for a bit now that neutrinos do this funky thing where they oscillate or switch between three different flavors. In Japan, a beam of neutrinos and a beam of antineutrinos were fired at a detector and compared.
Based on these results, there seems to be a higher chance neutrinos will oscillate than antineutrinos.
It's too soon to know if this will account for enough of a difference, but we'll see what happens. Another thing to look out for is this collaboration of physicists who are searching for evidence that the neutrino is actually its own antiparticle. Not only would this also explain the imbalance, it would usher in a whole bunch of physics that we have no way to explain. So here we are, against all odds, very much not annihilated and very much confused. Sadly, I can't give you a definitive answer today, but I can assure you that scientists are chilling deep underground with their fancy detectors as we speak. So hopefully, answers to why we exist are just around the corner.